we all know that the climatic variability is happening quite rapidly, and when this climate is changing, temperature is one of the key factors which is driving most of these changes. But some of the recent analysis have shown that it is a high nighttime temperature, that is the warming night temperature, which is more so important and is significantly predicted to induce negative impacts on crops, leading to yield and quality losses. But as of now, we really don't have a system that can actually capture these responses under the field conditions. So what you see behind me here is a prototype of something that we have developed, where we can actually introduce warmer nighttime temperatures and see how the wheat actually responds and if there is a reduction in an yield or quality. So I think if you look at this, Raju, at the top part of that's completely dry.
Right.
At the lower part, it's still a little bit green, right?
Yeah.
So if you are going to take some measurements, you might still get something at the bottom.
Yeah, I think this is a really important project because as we look forward in breeding, it's 10 to 12 years from the time we make a cross till we release something, and as we start to deal with these additional stresses, it's really important to have the tools to do that. So this project really sets the stage for us to evaluate materials, understand the genetics behind heat tolerance, and then look at new genetics as it comes along for its ability to handle these higher temperatures. And so I see this as critical information that feeds into breeding as it helps all the breeders, whether it's the K-State program or private programs or programs around the world, really understand heat tolerance and how to deploy it.
This is a starting step for a much bigger project. So we have a recently funded NSF EPSCO Track 2 project, where we are collaborating with University of Nebraska-Lincoln and Arkansas State University, where we are trying to look at two of the crops, wheat and rice, which are the most sensitive crops to warmer nighttime temperatures. So what we are trying to do here is a prototype of introducing that high night temperature on wheat and trying to study the physiological and the genetic responses. And this has been going on for about 3 weeks now. So we intend to have this sort of a stress introduced onto the crop for about 4 weeks, and after that the stress will be taken off, and then you actually start to see the impact. In the process of doing all this, we have taken a lot of physiological measurements, and a lot of spikes and the leaf samples have been taken. All these samples were taken at 4 o'clock in the morning when it was pitch dark. So all this will undergo molecular analysis to be able to come out with some markers that can be utilized for improving our wheat.
One of the most important aspects of the experiment is that we have our generator down over there, which provides power to each single tent. We've wired each heater up through that generator, so when we come out at night, we'll be able to roll down these sidewalls right here, which allows for keeping all the heat within the tent. And we also will shut these top vents as well. We'll be able to turn the generator on at that point, which gives us power to our electric heaters inside the tent, and also power to a fan which keeps the air circulating throughout the tent so we don't get any dead spots or any colder spots. The heater system is controlled through a computer system run by Raspberry Pi that was programmed by Dan Wagner. What it allows us to do is maintain a differential between the outside temperature and the inside temperature. Instead of setting a single set point of say 26 degrees for the inside, we're able to adjust the inside temperature to either 4 or 6 degrees above the outside temperature, which allows it to follow the same natural curve of the outside temperature and rate as it goes down in the middle of the night, then back up in the morning. So it gives a much more natural heat cycle through it and maintains that differential through it. At night, when we come to shut down the tents, we arrive around 7:15 to get everything started. The process begins with us going through and turning on the computer system and starting to roll down one side of these. Once we have the computer systems all up and running, we'll go to the generator, turn the generator on, which will give power to the fans and the actual heater. And we'll go back in, we'll check to make sure that the heater's running, the system's reading the temperatures correctly, and then we'll fully shut down the other side of the tent to start the heat stress. Our aim is to have that start about 8 p.m. every single night. And then the next morning, we meet at 5:45 a.m. and we start by shutting the generator down, and we open up each tent individually, and we'll have every tent open by 6 a.m. So all together, there's about 10 hours of heat stress each night.
The overall bigger aim of this project is to build much bigger tents of this kind to actually introduce much greater genetic diversity and also bring in the genetic components for the breeders to be able to have markers to develop our wheat, which is more resilient to high night temperatures into the future.